Okay, so there are a few rules for the protection layer. So that is very important while we consider. All these rules are mainly considered from the protection layers. CCPS book. So let us see one by one. Okay, sorry. So there is a first rule. IPL should act before event happens. So again, repeating the same basic source is CCPS book, that is CCPS LOPA 2015. That is a reference book. You can directly search CCPS LOPA 2015 book. So you will get the PDF book. So you can just refer that. So IPL should act before the event happen. So again, repeating back same example, monitoring of reaction and recording the temperature. So our event IPL should act before the event happen. In case of other events, alarm response, normally say there are few response time which is standard we are considering mainly we do the quantitative risk assessment. So in case of shutdown system, like we can say control system, we have the control valve and transmitter also, and in case of increase in the temperature, steam supply valve closed, that's the shutdown system or control system. So normally we consider the response time of maximum 2 minutes. 2 minutes means so suppose there is an increase in the temperature, pressurization there, so control valve get the signal, control valve close, there is a pressure in the reactor jacket, so normalizing the pressure. That total time is 2 minutes. Normally we consider it's a standard time for all the control systems. When there is a alarm and manual intervention, basically in that case, response time normally we consider 10 minutes. So whenever you define the protection layer, so you have to consider this response time. In case of alarm and operator has to go in the plant and close the valve or do some action, in that case response time is 30 minutes. So 2 minutes, 10 minutes and 30 minutes. So these are the standard time which normally we refer the purple book, that is for the quantitative risk assessment, that is available also. So that is the response time normally we should consider when we define or design the protection layer. So IPL should act before the event happens. In that case, suppose you have the shutdown system, you just have to see 2 minutes, you have to consider time and you have to check whether event happens before 2 minutes or after 2 minutes. Similarly, in case of alarm and operator response time, so 10 minutes, sorry, I think I just shared 10 minutes or 15, I forgot it. It's a 10 minutes. In case of alarm, there is a 10 minute. Means when there is alarm, operator will go to the particular console or DCS system. He will take the action, close the valve, whatever he has to do, normalization in the process. Complete time is 10 minutes, right? In case of alarm and operator has to go in the field and close the valve, that's a 30 minutes. So normalization takes 30 minutes. So you have to refer all these things before defining or identifying the protection layers. So that is the first rule: 2 minutes, 10 minutes, and 30 minutes. Right. Second rule is approach for deciding number of protection layer. Yeah. So basically, there should be the approach defined by the company for defining the numbers of protection layer. Basically, there are different protection layers. Like we have control system, SIS. We have mechanical safeguards. We have alarm and operator intervention or response. We have admin or passive. So how many? Suppose there are severity. Suppose we consider the severity 1 to 5. 1 is minimum, 5 is maximum, right? So in that case, first we have to define our system, risk management system, that in case of 1 severity, how many safeguards should be there. So say for 1, there is a 1 safeguard. Suppose we design that we require for 5 severity, we require 5 safeguards. For 4 severity, we require 4 safeguards. There is a basic risk matrix guideline. There is one international standard. I just forgot the name. If you require later on, you just can call me or send a mail to me. I will share all this presentation to you also. And if you require any reference document which I discuss in this presentation, you can send a mail to me. There is my mail address in the this presentation, and you can request for all this reference standards also. So there is a reference standard, international standard for the designing the risk matrix also. There is a RAST risk matrix for the consequence frequency, that is from the CCPS itself. In the CCPS, there is one guideline, standard is available, that is called the risk analysis screening tool, that is a RAST manual. I will share if you require, you just send me the mail. So based on that, normally we design these things. So say we design our risk matrix that if there is a 5 severity, we need a five minimum controls. Four it is required four minimum controls. Now we have to bifurcate our requirement. How many? Say in case of five CRT, we require five minimum controls. So how many control loops should be there? Minimum, maximum. How many alarm and operator intention we can consider? Admin or passive we can consider. So this is just example which is shared in this particular slide. If you see, there is a five severity. So preventive safeguard should be minimum 2. That is a basic requirement. If we take all the mitigative safeguards, so our actual risk assessment, we can say not, can be poor, we can consider this a poor or not adequate, because all are mitigative, so we don't have any cause for the prevention. So it means we are allowing cause to happen, then we are mitigating the our consequence. So minimum 2 preventive safeguard in case of high severity is always must. Few companies goes for 3 also. That depends upon the company and their particular progress in the PSM. Already established PSM, so I recommend 3 minimum preventive safeguards. Otherwise, you can consider the 2 also. So basically, we can club the controls SIS and mechanical safeguard. In case of 2 preventive, we can have 2 control systems or 0 mechanical safeguard or 1 or either way. So that is a basic requirement for severity 5. Then says why we consider 2 SIS, because if you check with your instrumentation team, normally always nowadays we design the DCS on the redundancy basis. If one system fails in one BPCS, basic process control system, second can be considered in operation. So redundancy, based on the redundancy of designing consideration in your BPCS or your DCS system, we are considering 2. Otherwise, we can consider only 1 only here. If there is no redundancy in BPCS, then we should design our risk matrix. In the case that severity 5, 2 preventive safeguard, 1 should be SIS and 1 should be mechanical. Because redundancy is there in the SIS, so we have the flexibility to select the 2 SIS or 2 mechanical also. Now, in case of 5 severity, alarm and operator intervention, maximum we should consider 1. Because normally 1 operator is always there for the 1 DCS system. That is a basic concept. So in case of 2, normally they are delivered to each other during the breaks. So at a time, normally maximum 1% presence during the breaks also. So alarm and intervention should be only 1 only. Admin and passive, we can have 2. So that's the basic requirement. So why we need 5 safeguards for the 5 severity, 1 safeguard for the 1 severity? You can just refer the right side of this table. There is a one figure which is self-explanatory. If there is a one initiating event, if there is a 4 layer in that, if initiating event pass through all the layer, that is escalation, that only it can reach up to the consequence. If any of these safeguards come, controls come in between that initiating event, so that helps to prevent or mitigate this particular event. So that is the basic requirement why we need 5 save controls in the 5 severity, 4 controls in 4. One, because in case of 1, 2, 3 severity, that is a minimal effect. Maybe in case of human, basically our main objective to protect the environment, human being and asset. So in case of 1, 2, 3 severity, it's a first aid case or hospitalization. So that we can say it's a recoverable. In case of 4 or 5 severity, normally recoverable possibility is not there. In case of human being also, in case of environment or asset. So that is why we are very careful in case of 4 and 5 severity. Right. So second rule is approach for deciding the number of protection layers. That is a basic thing. So you can refer the reference standard available from the CCPS, and you can define your this risk matrix. Now, third rule is basically layer of defense should be measurable and auditable. Demonstrate the performance. That is the basic thing. So again, this is based on the CCPS Low Pass Simplified Process Risk Assessment book. Measurable and auditable means say. In case of our fire and gas detection, suppose there is only alarm, so it's auditable. That alarm, if there is a record is available. But suppose in case of temperature control system, there is a graph, so it's auditable also. Measurable means we can measure the temperature. In case of fire and gas detection, it's a measurable, and we have to provide the graph also, or we have to provide the audible system at different locations where permanent fixed person available in the bench or workstation. So in this way, it demonstrate and demonstrate the performance also. So layer of defense should be measurable and auditable. So measurable means we should have the records graph or in the log sheets records with the frequency of recording should be based on our response time. So should be measurable and auditable. So just in case of layer of defense, basically measurable and auditable. Say for the manual case, basically in case of shut-off system automation, we will have the records graph also. So no concern there. But in case of manual monitoring, suppose we say temperature gauge. So temperature reading measurement is also required, and recording of the temperature in the log sheet is also required based on the response time. So in this way, this is a measurable and auditable. So demonstrate the performance. Rule 4, layer of defense should be independent. We have discussed a lot of example for the independent. Suppose we take, we have discussed, I think we discussed for the alarm also, but again we take the second for the control system also, because control systems are more reliable. So normally in case of severity 5, we require minimum 2 SIS. So in case of control system, suppose there is a same example, there is a feed of raw material because of some cause temperature increase, because of more flow of raw material, temperature is increasing. So in that case, we have the high pressure and high temperature alarm, and we have the control valve steam supply stop because of high temperature, because of high temperature and high pressure. Similarly, flow close because of high temperature, high pressure. So in here, in this case, suppose we say our first control is high temperature and high pressure, close the steam supply valve. So steam supply valve is 1, but detection is 2. So in this case, basically, because detection system, we have two system, temperature and pressure, which has a one action only, stop, close the control valve of the steam. So in this case, because we have only one control valve, so action is 1. So we cannot say there are two control system independent safeguards, two SIS independent, because action is only one temperature control only. In this case, our pressure and temperature, high alarm and control loop, close the control valve of the steam is not two independent SIS or independent protection layer, but it's one only. But when we stop the flow also with the pressure and temperature, so we have two action on the two transmitters, temperature and pressure. In that case, we can consider the two separate control system and separate protection layer. So that is the basic thing. Independent level of defense should be independent. That's the basic rule number 4. That is based on the CCPS low pass simplified process risk assessment. Now again, rule 5. Rule 5 is layer of defense have the different PFD and RRF. So this is again source CCPS low pass simplified process risk assessment. There is a one table. So different PFD and RRF. I already discussed that PFD is probability of failure on demand and RRF is risk reduction factor. Both are inverse. So suppose we take inverse to each other. Suppose we take one example, control system, SIS. Same example, there is a steam supply control valve and there is a high temperature alarm. High temperature, because we had a detector and high temperature alarm. So in case of high temperature alarm, that will close the steam supply control valve. So that's the one safety SIS we have, safety instrumented system we have, or control system we have in our this particular example. So in this case, as per our this CCPS LOPA book, there is a one table. Our probability of failure or demand is 10. We can consider 10 or one layer. And in this case, in particular for this particular SIS temperature control system, RRF will be 10 to minus 1. So you can see 10 or is equal to inverse to that RRF is 1 upon PFD, that is 10 to minus 1. So in both cases, your protection layer is 1. We can take one credit. So in suppose we are doing the risk assessment, we say our this runaway reaction severity is 5 and initial probability before the safeguard, before the control system, sorry, protection layer is say F1, that is a maximum. So when there is we consider this control system of the temperature, so this will be a PFD 10 or 10 to minus 1, means probability of failure will reduce. Initially we take F1 means once in a 10 year. So now because of introduction of this control system, probability of failure will be 1 into 100 years. So one layer will increase. So we can take credit of one layer and F1 will change from F1 to F2. F2 means once in a 100 year. F1 is once in a 10 year. Like that, we can take the consideration of PFD or RF. You can select anything. You can write down PFD also. You can write down RF. More easy is to write down PFD in the worksheet. 10, 100, 1000. That is more easy to write down. If you write down 10 raised to minus 1, so that takes more time. So normally we prefer to write down the PFD, probability of failure on demand. Now different layer have different PFD. Say for example, control system, say temperature control system, control valve and temperature transmitter complete loop. Normally it's a PFD is 10, once in a 10 year normally we can say. For PSV, there's a definition, clean system, so it's a once into 100 year. So PFD is 100. If it's a contaminated system, so normally we take 10 PFD. So there's a guideline already mentioned. Suppose in case of carcel open, carcel close valve, lock open close valve. So again, guideline is there. Suppose in case of we don't have any other safeguards in the system. There is not possible to even give the recommendation for additional safeguard. In that case, what normally we do, we have the control or loop system to increase the reliability of control system. Like we have temperature control system here. So we increase the reliability of that system. So there are few seal ratings, safety indicator level rating. So in case of seal 1, we consider again PFD 10, but we want to increase the layer, but we don't have any other recommendations for the control system. We cannot provide any additional control in the present system. So what we do, we increase the reliability. So we make it a seal rating 2. That means we change from 1 seal rating to 2 seal rating. That means we increase one layer. Means seal rating PFD is 10. So seal rating 1 PFD 10. So seal rating 2 PFD is 100. So we add one layer through increasing the seal rating or reliability of that control system. So this is another method, but in that way we can change the PFD and increase the PFD of that particular deviations. So this is the rule 5 which we follow. Now rule 6. Again, rule 6 is again source is CCPS book. Rule 6, in HAZOP and LOPA, consider failure of process control not a safeguard. But in case of HAZOP, normally it's allowable if we consider the failure of the process control. But of course, for safeguard we cannot. So in general, we can say in HAZOP and LOPA, consider the failure of process control only, not the safeguard or protection layer, right? So how we can understand this? Basically, say suppose our basic case study. We again go back to the case study that we have the reaction. We are adding 3 raw material A, B, C, and we have basically temperature control system. Suppose it's an exothermic reaction. So we are not heating the during the reaction, but we are adding 3 raw material. In that case, suppose we say raw material raw material A we are adding through the control valve. We are maintaining the particular flow rate of 1000 kilogram per hour. Our flow of A is 1000 kilogram per hour. So in that case, our basic this flow control system, that is raw material A flow control systems, that is our basically process control, not the safeguard, because we are adding the raw material through particular process control only. So in that case, we can take the failure of raw material A flow control system, and we can consider that as a cause. And of course, we can consider in other deviation, not this deviation of flow control, other deviation, we can consider that as a safe control system also, controls also like protection layer. But in case of suppose we are considering that other B and C raw material is properly depending upon the raw material A. So we have stoichiometry proportionate control in the raw material B and C feed. In that case, suppose we provide the flow transmitter there and control system there. So because flow of A change in the ratio, flow on B will also change. But that is a safeguard here, not a process control, because of basic process control, basic raw material is A, based on ratio of A, that B and C changes. So in that case, suppose B and C increase because of some other reason, flow of B or C increase because of some other reason, and that detect and stop the flow of B and C and stop the complete process or shutdown activates. In that case, we can consider this as safeguard. So in that case, we cannot consider the failure of that particular safeguard, and we cannot do the risk assessment, or we cannot do the our risk assessment exercise. So basically process control. The process control, if you say there are different layers for the process control, it starts from our basic process design. Normally first we do the basic process design without any controls. So that is we can say our manual process. Then we add the controls. It may be a process control, it may be a safeguards, maybe a protection layer. So then we add the controls. So in that case, then there is a third layer is alarm. Fourth layer is of our control system, that is SIF, temperature control, pressure control. Then there will be a mechanical safeguard. Then there can be a release system or gas detection. Then emergency response plan. There are different layers available for the protections. So in this case, our basic design and process control that comes in a basic process BPCS. So we cannot consider the we can consider the failure of BPCS during the HAZOP study, that when we consider the cause, but we cannot consider the failure of safeguard during the finding the causes, because safeguards we have high pressure alarm and control system, high temperature alarm and control system. So there, in that case, your basic flow controlled by raw material flow of raw material, and we have the control system. That is the basic process control system. Rest are the safeguards or control system. Protection layer, sorry. So basic process control, we can consider the failure during the finding the cause in the risk assessment, but safeguards we cannot fail, because our objective, as we discussed earlier, that if life of safeguard is 20 years, we have to do all the things to maintain the life of safeguard, maintain the objective deliverable through the safeguard for the 20 years. Means we will do the inspection, we will do the testing, we will do the preventive maintenance, all we will do to maintain that safeguard. So safeguard cannot fail, or protection layer cannot fail during the life cycle of that particular system. So that is why we don't consider the failure of protection system, protection layer or safeguard during the risk assessment. Of course, if it's a basic process control, we can take the failure of, we can consider the failure of that. Right? Suppose we maintain the level of particular time through the LT, then we can consider the failure of that level transmitter. But if a level is not maintained through the LT but by other some means, in that case level transmitter is safeguard or control layer, protection layer, so we cannot fail the LT in that case. So that's a basic difference between the process control and protection layers of safeguard. That's the rule 6. Now rule 7 is in case of redundancy of safeguard or IPL. In few cases, as I discussed earlier, the example, suppose we are providing the 2 pressure safety valve on the anhydrous ammonia, your LPG or other compressed gas storage tank. So purpose of providing 2 PSV there is for redundancy during the inspection testing. So in that case, we cannot take the credit of 2 PSV while doing the risk assessment, because during the testing, once in a 6 months, once in a year, we will review for 2 days or 3 days. So that PSV is not available throughout the 365 days, 24 hours. So in that case, we consider only 1 PSV as a protection layer or safeguard. So that's a basic thing. In case of redundancy of safeguard IPL, in few cases consider single layer of protection, like here on C. Similarly, suppose there are 2 control system as a control system, as a safeguard or protection layer, but our DCSS is not designed for redundancy, then we cannot take 2 protection layer as a credit, but we have to consider only 1. So that is the basic limitations of design system. In case of rule 7, again, rule source is CCPS, that is a book available. Rule 8, if 2 layer of protection in series, consider 1. Say, normally you have seen basically a best example, suppose we consider 2 NRV when there is a possibility of contamination in the liquid. So we are considering 2 NRV because of, in case of contamination, if any 1 NRV fails, second is available. So 2 NRV on the series. In that case, we cannot take credit of 2 NRV for the control, this protection layer or safeguard. We have to consider 1. The classical and best example, normally we install rupture disk in PSV, either before PSV or after PSV. So in that case, we cannot take the credit of rupture disk and pressure safety valve in the risk assessment, because when we install rupture disk before the pressure safety valve, so that is basically guideline of the S1 international standard. I forgot it, but I can later on just share the number also to you, that in case of contaminated fluid or liquid, normally we install the rupture disk before the pressure safety valve, so that first pressure, your rupture disc will break, and then pressure safety valve will pop up. So important thing to consider here, that suppose we are designing the pressure safety valve on 2 kg per centimeter or 2 bar. In that case, your rupture disc should fail on 2 or more than 2, because if fails below 2 and again it reaches to pressure safety valve, and of course if suppose we design rupture disc on 1.8 bar and it fails on 1.8 bar and it will reach to PSV and pressure will not reach to 2 bars, then in that case we have the issue that contamination will be there and later on PSV will not be available, or otherwise we have to make the SOP. Suppose we design RD on 2 and rupture disc on 2, so we have to make the SOP that in case of rupture disc, first we have to check the PSV also for the contamination before reinstalling the other rupture disc. So that is the first objective. Suppose we install rupture disc before the PSV, that is for the contaminated fluids, liquid or gas. Suppose we say our environment is corrosive, in that case we install the rupture disc after safety valve to protect our PSV from the environment, corrosive environment. So in both cases, same, both are in the series, so we have to consider only PSV as a control system, that is a safeguard or protection layer, not rupture disc also. So only one credit we can take, right? So if 2 layer of protection in series, consider 1 in that case. Ninth rule is 2 transmitter on same nozzle. Of course, suppose we have 2 transmitter on the same nozzle and both transmitter are connected with a different control valve, like pressure transmitter and temperature transmitter. Suppose there is a 2 transmitter also, temperature transmitter on same nozzle, and both are connected with different, one is with control valve, one is with XV, cylinder valve, on-off valve. So in that case, what happens, we have 2 different control loops, like one temperature transmitter is connected with control valve, separate loop, we can say loop 1. Second transmitter is connected with XV, on-off valve, cylinder valve, so second loop. Here we have 2 different independent loop, but transmitter is in the same nozzle. So in case of same nozzle, means if nozzle fails, detection will fail, so both loop will fail. So in this case also, we should consider only one loop as a credit for the protection layer or safeguard. So this is a basic thing. This is one example of a nozzle. So in that case, we have to check independency of the protection layer in all the aspects. Your installation should also be considered, your design of loop, installation of loop. Installation should confirm that different transmitter is different, independent of each other. So that is a basic concept for independent protection layer. Same reference of CCPS LOPA 2025. So these are the basic rules for defining the protection layers. Of course, response time is very important in all the cases, all the rules. So that is a basic for all the rules. That is a rule 2, but applicable for all the rules, rule 1 to 9. So please consider response time in all the cases when designing the protection layers also. So these are the few rules, basic rules for the protection layer.